Hello everyone! Today we will present an innovation simulation program for the motion of ideal gas molecules. This tool uses numerical simulation and AI technology to make abstract physical concepts intuitively visible. What you are seeing is the random motion of gas molecules in a container. The movement and collision of each small ball are precisely presented in real-time calculations. In traditional physics teaching, students often have difficulty understanding. Why does random motion of microscopic molecules result in macroscopic pressure and temperature? How is pressure generated? What is the essence of temperature? Why do gas laws hold? Our program is specifically designed to address these teaching difficulties. Let's look at the background of this experiment. A hot air balloon can ascend. The burner heats the air inside the balloon, increasing the temperature T. At the beginning of the heat process, the balloon's opening is open, and the internal pressure P is basically equal to the external atmospheric pressure. P remains constant. According to the quotient PV, the unity with the increasing and P remaining constant, the volume V of the balloon expands. As the volume V of the balloon expands, the weight of the air is displaced, becomes greater than the weight of the balloon itself. First, open the interface. The main part is a sealed container inside which there are some stationary molecules. On the right side is the parameter adjustment panel, showing the real-time status. AI for data analysis and some explanatory notes. Below the container is the right distribution graph, and further down are some real-time physical quantities. Now we click Start Simulation to begin the experiment. You can see that our experimental program can visualize the molecular motion, trajectories, and the collision processes, which is more conducive to observation and understanding. At the same time, the rate distribution graph below and the Maxwell curve are visually compared. When temperature is increased, the distribution curve becomes gentler, and the peak shifts to the right. The rate distribution exactly conforms to the Maxwell distribution curve. This highlights the relationship between molecular velocity and the energy and temperature. The number of molecules can be adjusted. The more molecular there are, the greater the pressure. This is the number of impacts per unit time increases, and the impact force also becomes greater. This successfully demonstrates Avogadro's law. Ideal gases have three laws. First, let's look at Raoult's law. The pressure of a gas is proportional to the thermodynamic temperature. When keep the container volume constant and just the temperature, it can be found that when temperature increases, the pressure increases. Next is Boyle's law. The pressure of the gas is inversely proportional to the volume when the temperature remains constant. When I keep the temperature constant and adjust the container volume, it can be found that the larger the volume, the smaller the pressure, since the size of our container cannot be manually adjusted. The Gay-Lussac's law will not be discussed for now. In advanced deciding, we adjust the size of molecules, and it can be found that the larger the molecule, the higher the collision frequency. This perfectly interprets the gas kinetic theory. We have used a quadri two-dimensional space partition structure here, which reduces the time for collision detection. When we turn off the quadri, the detection time is approximately 0.4 milliseconds, and when we turn it on, the time drops to around 0.1 milliseconds. This is conducive to more accurate data analysis and ensures the success of the experiment. Now, we start adjusting the volume. Here, the AI will automatically skip repetitive and small changes in data and automatically collect data. Collecting more than 5 sets of data allows for fitting. We recommend collecting several more sets to achieve better and more realistic fitting results. you need specific data, you can click Export Data, and the web charge will automatically download the data table to your computer, which can be opened directly. In terms of technical implementation, we have several outstanding features: pure front, and implementation HTML5, plus JavaScript, no backend required. Next, real-time calculation, response time less than 3 seconds, precise physical model, elastic collision, energy conservation. Then, AI-assisted analysis, automatic data fitting. In addition, cross-platform compatibility works perfectly on mainstream browsers. The educational value of this program lies in making the abstract concrete, visualizing macroscopic processes. The second, interactively exploration. Students can conduct experiments independently. The third, data-driven. A complete understanding from phenomena to laws. The fourth, AI-empowered. Intelligent analysis to assist learning. Next, we move on to the part of program refinement. The program can further introduce molecules of different masses and can adjust the proportion to observe the effects of pressure and temperature. The program can incorporate phase change simulation, simulating gas liquefaction. At the same time, interdisciplinary application scenario can also be added, such as aerospace. In this process, we use the cursor to primarily responsible for programming and DeepSeek to refine the introductions. Title. First, clearly describe the requirements in stages. Second, precise description of physical principles, including conservation of momentum, elastic collision, etc. Third, interactive optimization and continuous dialogue. Fourth, conduct tests, intensify problems and find repairs. It is not just a demonstration tool, but also a platform for exploration and discovery. Through this simulation program for the motion of ideal gas molecules, we have successfully integrated numerical simulation, AI technology, and physics teaching. It breaks through the limitation of traditional experiments, allowing every student to explore the mysteries of physics at their fingertips. Thank you for watching.